Okay, let's get started here. We are going to talk about differentiation. We're continuing on with the chapter. We're actually in section 4, and what we're going to talk about today is the chain rule. We've talked about it in class. This is probably the most powerful tool in taking derivatives in calculus. I hope you agree with me as you see what we're going to do. Okay, so the objectives of this lecture. First, what we're going to do is find the derivative of a composite function using the chain rule. Of course, I have to explain the chain rule first. And then take the derivative of a function using the general power rule, which is a very straightforward and great application of the chain rule. And then we're going to simplify derivatives using algebra. I'm going to step through that quickly in this presentation, and in the next presentation we'll actually do some examples and take more time for those. And then we will find the derivative of trigonometric functions using the chain rule. Okay, so the chain rule, simply put, the chain rule allows you to take derivatives of composite functions. So what that means is, without the chain rule, you could calculate the derivative of x squared minus 1. Now you can do the square root of x squared minus 1 and know how to deal with that. Sine x, remember the derivative of sine x would be cosine x. But when you get sine 6x, because that's a 6, we don't have any rules to deal with that. And the same thing down here with tangent x squared. So what we're going to do is, in applying the chain rule, it's actually written down here, dy du times du dx. The du's will cancel, and you end up with dy dx. So really what we're doing with a composite function is we are putting an intermediate step in there, and let me show you an example of how that works. So you have a set of gears, and this is similar to the example we used for a composite function. If you turn axle 1, how fast does axle 3 turn? How many times do you have to turn axle 1 to get axle 3 to go around 1 time? So axle 1 has a radius of 1, axle 2 has a radius of 3. So change in y for change in u. So how many times does y have to go around for u to go around 1 time? And it's 3. Every 3 times gear 1 rotates, gear 2 rotates 1 time because their circumference is 3 times greater. Because their circumference is 2 pi r, so it's a ratio. Every time gear 1 goes around 3 times, gear 2 will go around once. Now, when axle 2 spins, you've got gear 3 turning gear 4. And again, this is 1 and 2, so gear 3 has to go around 2 times in order for gear 4 to go around once. So what this tells you is this goes around 3 times, this goes around once. But this has to go around twice to get this to go around. So for this to do once, this has to go twice. For this to go twice, this has to go 3 times 2, or 6. Kind of confusing, but I'm going to step through a couple of slides that explain it a little bit more. So the circumference of the second gear 3 times greater than the first. First axle must make 3 revolutions for the second axle to turn once. Similarly, the second axle must make 2 revolutions for the third axle to turn once. So dy du is 3, du dx is 2. Combine these two results. The first axle must make 6 revolutions to turn the third axle once. That's composite functions. So that explains composite functions, but we're looking at rate of change, dy, change in y, over change in x. Y has to go around 3 times. For u to go around once, u has to go around twice. For x to go around once, 3 times 2 is 6. So that is the basic construct of how the chain rule works with u substitution. And we're going to look at how to do that. We're going to look at another way as well. But what this really deals with is change in y with respect to u times change in u with respect to x. And that is written right here, which is a fun way, and we'll have to use that quite a bit later on. But what we're going to use mostly in this section is the derivative of your composite function f of g of x is f prime of g of x times g prime of x. And yes, the algebra does get pretty intense, but let's take a look and see this. So if y is 1 over x plus 1, if we make u equal to x plus 1, now y is equal to 1 over u. You have a rule for this. Oops, let me go back. You have a rule for this, and you have a rule for taking the derivative of this, so you just need to combine them properly. Same thing, you don't have a rule for sine of 2x, but you know how to take the derivative of 2x, you know how to take the derivative of sine, and then the radical, and then the tangent. So let's look at the general powers rule. This one is great. So if you have some function raised to the n power, this is just like the power rule. You bring the exponent down, reduce the exponent by 1, leave what's in the parentheses the same, but then multiply it by the derivative of whatever's in the parentheses. Let's look at an example. So we have 3x minus 2x squared all to the third power. So what we're going to do here is we're going to take this is u to the n. So we're going to bring the 3 down, raise that to the second power. We don't change what's in it. 3x, that's supposed to be a 3x minus 2x squared. Then we multiply it by the derivative of what's on the inside. So that's 3 minus 4x. So this slide's actually going to step you through those steps. I just saw it. So there's the u substitution. So f of x is equal to u to the third. So here's your u. Bring the 3 down, u to the second, times the derivative of the u. Kind of what I did up here, but then you simplify it. Take the derivative, multiply everything out. Okay, now we're going to talk about simplifying, which is the algebra. So there's your original function, and what we're going to have to do for this, because we have a couple of different parts, we've got the x squared, and then we have this. You're going to use the product rule, this times this, but you're going to have to use a chain rule for that polynomial under a square root. So we'll rewrite it in exponential form, and then here is the product rule. First times the derivative of the second, second times the derivative of the first. But to take the derivative here, we're going to have to apply the chain rule. So it's x squared. The chain rule, bring the 1/2 down, write what's in the parentheses, subtract 1 to the negative 1/2, then the derivative of u here is negative 2x. Now, I don't necessarily show my work the way the book does in the examples. I'm taking you through the way the book does it, and in the next video I'm going to show you how I would do it, and then you continue with the derivative over here. And at any point, if you need to stop to look at it, to follow, that would be probably a good thing to do. Okay, simplify, factor out, and simplify. And remember, you can leave a radical in the denominators. We're going through and doing this. So there you go. Here's another one we're going to do, simplifying the derivative of a quotient. So you're going to have to use the quotient rule with the chain rule for the denominator. First, we're going to rewrite it in exponential form. Then it's low d high minus high d low all over low squared. The derivative of x is just 1. The derivative of your denominator is 1/3. What's in the parentheses, x squared plus 4. And then 1/3 minus 1 is negative 2/3. And then what you have to tack on at the end, this part that you tack on is the derivative of what's in the parentheses. So that's the chain rule part within the quotient rule. Then we're going to go ahead and simplify. And simplify again, and there you go. So you're simplified. Now, okay, so we're going to use the general powers rule here, but when you take the derivative of what the u is, you're going to have to use the quotient rule. So you have u is what's inside the parentheses. Bring the 2 down, the exponent becomes 2 minus 1, or 1, and then take the derivative of what is inside the parentheses. Well, of course, that means you do the quotient rule, so it's low derivative of the high minus high derivative of the low, all over low squared. Now you're going to multiply everything together, and your denominator now becomes x squared plus 3 to the third. You'll notice here it was squared, and then the third, and I hit a wrong button again. and your numerator, you'll notice that they leave some of these in factored form. And these are just look through the book to look at the examples to see what they leave in factored form and what they don't, because leaving it factored is the way to go when you're doing the chain rule, and it ends up being a much easier way to approach the problem. Okay, trig functions in the chain rule. This is very straightforward. Derivative of sine u is cosine u du, the derivative of u. So if you're doing the cosine of 2x, if you're doing the derivative of sine 2x, it's cosine 2x times the derivative of 2x, which is 2. So we'll just go through a couple examples quick. So sine 2x is cosine 2x times the derivative of 2x, which is 2. So it's 2 cosine 2x. Derivative of cosine x minus 1 is negative sine x minus 1 times the derivative of x minus 1, which of course is 1. Tangent 3x, the derivative is secant squared 3x times the derivative of 3x, which is 3. I stepped through those quickly. Here are the trig functions and the chain rules that we have covered so far. You need to know all of these from memory, except maybe these trig functions, the ones that I'm circling, because all of those trig functions can be derived from those two using the quotient rule. So I'm not going to spend a lot of time here. Just realize that these are all the things that you are now responsible for knowing.